और भी जगह पर है, जैसे यूके में भी है सेक्रेट, तो और भी जगह पर है। गुड मॉर्निंग टू ऑल।
Good morning, Mr. Agarwal.
Good morning, sir. How are you, sir?
Fine, fine.
Thank you, sir.
You cannot say that I am not attending.
You are available, sir?
I am available, no?
Thank you very much, sir. My pleasure. I am obliged. You are here. Thank you, sir.
No. It is part of my duty.
Thank you, sir. Thank you very much. Today we are having, sir, very important topic which is related with the the power grid and its grid automation. How we are doing this? Dr. Avni Khatkar from National Physical Laboratory, the senior scientist of National Physical Laboratory, is basically taking this program today onwards. Ma'am, can you kindly open your camera, please?
Yes, sir. Good morning, everyone.
Good morning. So we have with Dr. Avni Khatkar, who is working in the National Physical Laboratory and in the LF and HF voltage, current and microwave metrology. Metrology, Indian Standard Time Division. Oh, very good. You are working in the time division also.
Yes, sir.
She is a gold medalist in her master's degree and completed her PhD in electronics and communication engineering from University Institute of Engineering and Technology, MD University, Rohtak. She has published more than 50 papers in international journals of great repute like Springer, Elsevier, IE, etc., and has participated in more than 35 national and international conferences and workshops. We are obliged you are here. She has been awarded as the best presenter in many conferences, including an award by Dr. APJ Abdul Kalam in Science Conclave, ISCA Best Poster Award in 2016 by former Prime Minister of India, Shri H.D. Devagowda at the University of Mysore. She is a life member of Indian Science Congress Association and Metrology Society of India. Thank you very much, ma'am, for accepting our request to deliver your lecture on this very important topic, which is related with the power grid. And certainly, when this time dissemination will start in our country, this problem of phasor will be sorted out, and we will be having, because I hope that we are having the energy or the power more than that which we actually require, but due to a lot of problems and losses, etc., we are not able to cope up our requirement in the villages and at some places. But still, we hope the better future. We have with us our honorable director, sir, Shri B.N. Dixit Sahab. I would like to request him to kindly inaugurate this workshop, so please.
So I feel very happy to join the August meeting, and it is very hard work of Mr. Ashutosh Agarwal that he is organizing every week such nice program on various topics. And today this topic is on power grid is also related with the time dissemination. And the time dissemination work is, we have made the agreement to achieve this with the National Physical Laboratory as well as and with the ISRO. So this power grid system is also relating the matter of the time dissemination. And today, since we don't have the time dissemination, so the grid that dissemination system is not available in our country. So in our country, so suppose that in one city or in a commissionerate, there are some grid are there through which the power supply is going on to all the consumers. And if somewhere the failure is there, it is not known that why such failure is there. If the time dissemination systems will be applicable, then the point of failure will be also known there. Whether it is through the grid systems or whether through any transformer or any other points where the power supply line has been gone. So, this is a very good topic and interesting topic for all the peoples, including the industry, laboratory, consumers, all these stakeholders, because the power uh, supply effect is on everyone. If you have good power supply, quality power supply, then your instrument will function long and for the longest time and with the super quality. And we do not have such type of thing, then your industry may not produce the quality product because they do not having that backup of such electrical background. So the manufacturing defects will be available there, and they may not uh, get that very competitive things which is at present available with the international competitors there. Because a lot of international competitors are available in our country, and we are also doing same to them. So, and we are depending on some other technology. And that Dr. Hitkar will today provided information
रौनक इसको आप ऑपरेट करो बेटा वहां से माइक को
that how the systems is going on there. So I feel very proud that today that I got the opportunity to integrate this very uh, seminar and meetings, and I hope that all people will be benefited. And I am happy that Mr. Agarwal from the Department of Consumer Affairs and RSL Ahmedabad is making such programs every Saturday. So welcome, Dr. Avni Khatkar. I hope that your good words and your knowledge will be benefited to all the consumers and stakeholders there. Welcome, madam, please.
Thank you so much, sir.
thank you very much sir we have with us Dr. Sanjeev Kumar ji, who is from IDMI today, and Dr. Mandal from National Physical Laboratory at RSL Ahmedabad. They are here to support us, to guide us in this field of metrology to do better. And with this, I would like to request, Madam, please kindly take over and let us enlighten us with your knowledge and the experience whatsoever you have. Please, ma'am.
Thank you so much, sir, for providing me this opportunity to present my ideas and interact with all who are present here. And I especially thank Dr. Ashutosh Agarwal, sir, for providing me this opportunity. And as you all know, that the title of today's workshop is Grid Automation, that is the future of Indian power grid. And I, being from a Metrology Institute of India, will focus on the role of metrology in this very area. Actually, this automation of the Indian power grid is a crucial step in the modernization and transformation of the power sector in India. And this automation can help improve the efficiency, reliability, and sustainability of the power grid. A task force was set up in September 21 by the Power Ministry to suggest the ways for the modernization of the transmission sector and to make it smart and future ready. And recently, the report of this committee was accepted by the government. And this report also emphasizes that modernization of the transmission grid is vital to achieve the government's vision to provide 24 into 7 reliable and affordable power to the people and also to meet the sustainability goals. So, as we move ahead in today's workshop, we will talk about a bouquet of technological and digital solutions which can be adopted to make the transmission grid future ready. So, first of all, I'll start with sharing my slides. Are my slides visible?
Yes, ma'am. It is very well visible.
Okay. So I will
It is
start
visible.
with today's presentation.
मैम ये
on
पॉसिबल है तो फुल स्क्रीन मोड में करेंगे प्रेजेंटेशन मोड
it is in presentation mode.
नो मैम फ्रॉम हियर
Now it is in presentation mode.
नो प्रॉब्लम मैम कंटिन्यू
I guess because I have opened this in the browser mode, that's why it's not going in the presentation mode maybe.
ओके
So it's not coming in the presentation mode. So we will talk about the grid automation and the future of Indian power grid. First of all, we will see the importance of measurement. Nowadays, the measurement is more valuable than ever, and we depend upon measurement for almost everything, right from timekeeping to weather forecast, from our day-to-day work at home to heavy-duty manufacturing and industrial research, and also in medical science. So when we talk about measurements, the uncertainty in measurements also come into picture because no measurement is ever guaranteed to be perfect, and uncertainty of measurement is actually the doubt which exists about the results of any measurement. And we should never confuse uncertainty of measurement with error, because error is actually the difference between the measured value and the true value of the object which is being measured, whereas uncertainty is the quantification of the doubt about the measurement result. And by quantifying the possible spread of measurements, we can say how confident we are about the result. And on May 20th, 1875, Meter Convention was set and they established BIPM, that is the international organization, and India became the member of BIPM through National Physical Laboratory in 1956. BIPM is actually the home of International System of Units and the International Reference Time Scale. Now, before going into the talk, I will first talk about the mission, vision, and mandate of CSIR NPL. CSIR National Physical Laboratory is mandated to be the India's National Measurement Institute by an Act of Parliament and is the custodian of the national standards with the responsibility of disseminating the measurement traceability as per the needs of the country. And CSIR NPL provides apex level calibration services to various industries, strategic sectors, academia, government, and non government agencies. And these accurate and precise measurements will support Made in India and Made in India products and the Indian industry and businesses to innovate. By developing the India's measurement standards, which are internationally accepted, and by disseminating the measurement traceability to the industry, government, strategic, and academia, we can unpin the India's prosperity and the quality of life. And CSIR NPL participates in international intercomparisons with a mission to establish the primary standards so that India remains at par with international measurement laboratories. When we talk about metrology, we should see how metrology is there for the inclusive growth of India and for the quality infrastructure. The we have international organizations also and national organizations also for metrology. At international level, we have BIPM, APMP, and OIML. Similarly, at national level, we have NPL and the Legal Metrology under Ministry of Consumer Affairs. Similarly, for standards, we have ISO and IEC at international level and BIS at national level. Similarly, we have accreditation bodies too. Now, at CSIR NPL, we have
हेलो
the
एक्सक्यूज मी मैम, आपकी स्लाइड मूव नहीं हो रही हैं।
move नहीं हो रही है।
हाँ अभी हुई है।
अब move हो रही है।
यस यस
Are they
मैम,
moving now?
यस यस यस।
Okay. So at CSIR NPL, we have the SI unit of measurement wall, which depicts the relationship between the SI units of measurement and the fundamental constants. Similarly, we have the metrology traceability pyramid, and traceability is unbroken chain of measurements, and this pyramid shows this unbroken chain of measurements which are traceable to the SI units, and also shows all the responsible organizations in India for the dissemination of metrological traceability to the manufacturers and to the end users. So we can say measurement is the first step which leads to control and eventually to improvement. And if you cannot measure something, you cannot understand it. And if you cannot understand it, you cannot control it. And if you cannot control it, you cannot improve it. So now coming to the electric grid. Electric grid is a network of synchronized power providers and consumers that are connected by the transmission and distribution lines and are operated by one or more control centers. The electric grid has basically four components, that is generation, transmission, distribution, and consumers. Generation can be either through thermal, hydro, nuclear, and now we are also focusing on the renewable energy sources. Transmission is through high voltage AC or DC. Then again, distribution is can be through AC or DC. And then we have different types of consumers depending upon their needs, like domestic users or industrial and commercial users. Now, when we talk about the Indian national grid, the grid management of India is not a new concept, and it was started in early 60s. And this grid management started on a regional basis then. And all these state grids, they were interconnected to form the regional grid in early 60s. And India was demarcated into five regions, namely northern, eastern, southern, western, as well as the northeastern regions. Then in October 1991, these northeastern and eastern grids, they were also interconnected. All these interconnections were done so that we can reach up to a point where we can have a one nation, one grid, and one frequency. So seeing that concept again in March 2003, western region and the eastern region, as well as the northeastern region, they were also interconnected. And in August 2006, the north and east grids, they were interconnected. Thereby, now we had four main regional grids, that is the northern, eastern, western, and northeastern grids. And these all grids, they were synchronously connected in on August 2016 to form a central grid which was operating at one frequency. Now, in December 2013, the southern region that was also connected with the central grid in synchronous mode with the commissioning of the 765 kilowatt Raichur Solapur transmission line. Thereby, the Indian grid achieved one nation, one grid, and one frequency. Now, when we talk about the Indian power system, as we have seen that it achieved one nation, one grid, and one frequency in December 2013. And we all know that the global power demand is rising exponentially in both developed as well as the developing nations with the development of technology. Similarly, India is also witnessing a higher energy demand as per the 19th survey of electric power during 21-22, which may be attributed to the establishment of new startups in India under vocal to local and make in India initiatives of government of India. So more specifically, we can say that we need to upgrade the existing national grid, which is a network of synchronized power providers and consumers which are connected by transmission and distribution lines and are operated by one or more control centers to a smart grid. Now, the question arises how to make this national grid smart. So, the digital technology which allows for two-way communication, and this two-way communication is between the utility and the consumers, which are interconnected by transmission and distribution lines, and we have sensing all through the transmission lines will make the grid smart. And this energy and communication interface will together conceptualize the smart grid operation. We have different smart grid definitions also. As per the US Department of Energy, Grid 2030 envisions fully automated power delivery network which monitors and controls every customer and node, ensuring two-way flow of information and electricity between the power plant and the appliance and all point in between. And as per the International Electrotechnical Commission, the smart grid is a developing network of transmission lines, equipment, control, and new technologies working together to respond immediately to our 21st century demand for the electricity. So now if we talk about the main differences between the existing grid and the smart grid, so presently we have electromechanical grid, whereas we are focusing towards a digital grid in which we will be having a two-way communication. That means the consumers can also interact in this grid. Till now, in the existing grid, we only have centralized generation, whereas we are focusing towards having a distributed generation. Till now, in the existing grid, we have limited number of sensors, manual monitoring of the grid, because of which the existing grid is more prone to failures and blackouts. So, in order to remove or to minimize the failures and blackouts, we are moving towards having sensors throughout the grid so that it can be self monitoring. We can have the concepts of adaptive and islanding so that the blackouts do not come across the complete grid and they can be islanded to a small locations. We are focusing towards having a pervasive control and towards a self-healing sort of smart grid. Now, when we talk about the smart grid, we in these smart grids, wide area monitoring systems, that is WAMs, they play a crucial role by capturing the measurements in the power grid over a wide area and across the traditional control boundaries, and then using these measurements to improve the grid stability and events through wide area situational awareness and advanced analysis. And these wide area monitoring systems, they use GPS satellite signals to time synchronize all the PMUs which are being placed in these wide area monitoring systems at all the important nodes in the power system, and then they send the real-time phasor, that is both magnitude as well as angle, to the data centers to control the complete grid. And these acquired phasor data, they provide the dynamic information of the power system and helps the operators to initiate any type of corrective actions which are needed in order to enhance the power system reliability. And this early warning system, it contributes by increasing the system reliability, by avoiding the spread of these losses in a larger area, and to control the large area disturbances and optimize the use of assets. When we talk about wide area management, wide area protection also comes into picture. Initially in conventional protection systems, all the decisions, they were made on local measurements. Because of these local measurements, it was very difficult to secure and to maintain the stability of large power system networks. So now, wide area measurements, which are based on protection, it was developed so that we can have a wide area protection system which can perform online security analysis, and we can also have a post disturbance analysis of the complete system. Now, by having these WANs technology in the grid, it is very much beneficial for the grid operation because it provides in-depth insight into the power system behavior and elements. It brings efficiency in operation as well as in the economy, and it will also enable efficient calibration of all the measuring equipments. And it will also facilitate integration of large quantum of intermittent and variable renewable generation into the grid. And this also enables synchronous measurement of real-time grid parameters across the widely spread grid with a lower latency in data transfer and to control centers, which would be very effective in reliable, secure, and economical grid operation. And it also provides more intelligent and dynamic information to special protection schemes, which will be a step towards having a self-healing grids. Now, as we all know, as India is moving forward into a smart power transmission system, which features such real-time monitoring, so it also provides many benefits to the society. And these benefits are very substantial. These benefits will help in the improvement of mainly the reliability. So by having a more reliable network, it will help in reducing the occurrences of any interruptions and power quality disturbances, and thereby reducing the probability and consequences of any widespread blackouts. And it will also help in developing the economy and efficiency, because by using these networks we can use all the elements and the entire grid in all to the maximum capacity of all the elements which are being used in the grid. And it will be also environmentally beneficial, because by using this we will reduce the emission of carbon content to the environment, because we are focusing on moving towards a greener grid. So by having a larger penetration of renewable energy resources into the grid, we will have a reduced number of emissions, and it will improve the efficiency of the generation, delivery, and consumption as such. So by having this automated operation of grid, we will be having a better situational assessment. We will be having a capability to have increased share of renewable capacity into the power mix, and this enhanced utilization of the transmission capacity and greater resilience against any cyber attacks as well as any natural disasters, and having this centralized and data driven decision making and reduced enforced outages through self correcting systems, it will be very beneficial to the society. And this fully automated, digitally controlled, fast responsive grid, which is resilient to any cyber attacks and natural disasters, is the need of the hour. And this system should ensure isolation of specific areas in case of any contingency, so as to protect the grid and prevent larger outages. Now, after talking about the benefits, as we know, till now we are focusing on the SCADA systems, and now we are moving towards having phasor measurement units into the system. So the SCADA systems which were used till now, they are built upon 104 RTUs, and they are used in till now in the present grid. So this present grid, it is primarily managed by using technologies like SCADA, that is supervisory control and data acquisition. And this SCADA system, it has a refresh rate of 2 to 4 samples per cycle, and hence it provides only a quasi-static grid visibility. So when we use a normal 104 RTU in the SCADA system, it will send readings every few seconds, and it can be used to read the voltage, current, frequency, breaker status, etc. in a substation. However, due to its very quasi-static nature, it cannot be used to read or compare phases, that is the phase shifts in the grid. So a SCADA system which is built on this, it cannot be used to reliably monitor the health of the grid and to isolate the trouble spots of the grid. However, if we have a PMU based system, a PMU, it can continuously stream data with an absolute timestamp at a very high rate, for example 25, 50, 100 or even 200 frames per second, and this faster speed, which is over 100 times faster than a traditional SCADA system, we can measure the dynamic nature of the grid, and this streaming data which is collected from multiple PMUs, this can be used to develop a customized sophisticated algorithms which can be further used to allow the load dispatch computers in order to completely and continuously monitor the grid at the regional levels and automatically perform the task of islanding, load shedding, and disconnecting the zones which can cause any disruptions and potentially threaten the stability of the grid. So by using phasor measurements in the grid, we can ensure optimum grid synchronization and may also be effectively using the grid by having the islanding detection systems, by having system blackout restorations, by having microgrid management, by enabling the power system operation to optimize the energy, and we will also be having cost efficiency of the grid in this way. And the PMU data which is collected, this can be used efficiently by the grid operators in order to monitor the real-time grid conditions and the phase angles so that we can optimize and push more power through the existing transmission lines and transformers. Hence, by using the precise load balancing techniques, we can use the existing infrastructure to their maximum capacity. So by using a PMU, we are also getting wide area monitoring systems. So we are getting early warnings about our asset conditions, and complete stability or the grid picture is there if we are using phasor measurement units. So now when we talk about phasor measurement units, synchronized sampling comes into picture. And when we talk about synchronized sampling, we need to have all the samples of the grid. So for that, for detecting the fault detection process, we require at least 6 fault loop equations for all the upcoming samples in the power system to have to see all the faults which are existing in the power system. So different faults can be there. 3 types of line to ground faults can be there. 3 types of line to line faults can be there. 3 types of line to line ground faults can be there, or line to line triple line or triple line to ground faults can be there. So all these faults can be detected in a power system by using 6 fault loop equations. And these instantaneous values, they are converted into phasors by using phasor estimation algorithms. And when we talk about phasors, what is a phasor? Phasor is actually a complex equivalent of a sinusoidal wave quantity such that the complex modulus is the cosine wave amplitude and the complex angle is the cosine wave phase angle. So we are talking about the phasor in this. And through phasors, the power system state analysis can be done, both for the stability analysis and for the transient state also. And by using this concept of symmetrical component theory, this fault analysis calculations, they can be carried out by using single equation also. And These positive sequence voltages of a network, they constitute the state vector of the power system, and hence the phasors which are obtained from each three-phase signal, these phasors, they must be sampled precisely at the same instant, and this precise sampling of the phasors at the same instant is what is known as synchronized sampling. And by having this synchronized sampling, we get synchrophasors. Synchrophasors are nothing but the phasors which are representing the fundamental of an AC signal, whose magnitude is actually the RMS value of the fundamental amplitude, and angle is the difference between the signal fundamental angle and the phase angle of the cosine at the nominal signal frequency, which is synchronized to the UTC time. Now, when we talk about this synchronized sampling, for small distance, this synchronization could be carried out by using common sampling pulse to measure all the measuring systems. However, it is very difficult when we when we see a larger distance or when our complete grid is connected. So to solve this problem, PMU comes into picture. And by having this synchronized sampling, we have many types of applications which can be solved. For example, state estimation, adaptive relaying, fault and disturbance recording, instability prediction of the power system. So now what is this PMU? PMU is actually a device, or it can also be a function in a multifunction device, which can produce synchronized phasors, frequency and rate of change of frequency, that is ROCOF, estimates for the voltage or current signals and a time synchronization signal. These phasor measurement systems, they actually trace their origin to the development of SCDRs, that is symmetrical component distance relays, of early 1970s. And in early 1980s, measurement system started using the GPS to synchronize the sampling clocks, which offers a common time reference. And the first experimental PMU, it was developed at Virginia Tech University in 1988, and Metrology was the first company to build the first PMU in 1992. So these PMUs which are developed, they measure synchronized phasors, and they measure the positive sequence voltages, currents, and which is time synchronization, which has time synchronization at all the different locations, and they compute these phasors by utilizing very fast recursive discrete Fourier transformation algorithms. And as I've already told, they are time stamped at the source, so data transmission speed is also not critical in it, because all the measurements, they are time stamped at the source itself. And at power grid, the time variant sources and loads, they introduce a complexity and disturbances which can threaten the stability and reliability of the power grid. And in order to maintain this reliability of the electrical generation, transmission and distribution, real time computer control of the grid is required. Initially SCADA was used. Now worldwide, the power grid is moving towards the concept of phasor measurement units in order to deliver real-time critical data on voltage, current, frequency, and phase. And these PMUs, which are used in the power grid, they are so much important because they are providing all the information of the grid. So these PMUs, they must be calibrated in accordance with the latest standard, that is IEEE 602-55118 2018 standard, so that the data which we get from these PMUs is consistent, accurate, and credible, in order to remove all the barriers for their adoption by the power sector. And being an NMI, it is the prime responsibility of CSIR NPL to establish the phasor measurement unit calibration facility, which is a national standard, and to disseminate its traceability to the nation. Now these PMUs, they are being used in order to see any grid event or the failure of any grid, and as they are being installed in the power grid for real time measurements, and they provide all the necessary situational awareness to the operators. So this technology plays a very crucial role for the future advancement of the power grids of different dimensions by keeping track of the grid's health, by handling blackouts, and by reducing the outages. Now, if we see the present status of PMUs in India, and as we all know that the Indian electricity network is one of the world's largest synchronized grid, which has a capacity of around 400 gigawatts. And actually in June, July 2012, India suffered the world's biggest power blackout due to a grid failure. And this blackout, it affected more than 620 million people across 22 states. So after this blackout, a committee of international experts was formed by the government of India in order to minimize the future possibility and the impact of the grid failure, and to recommend what all solutions can we have in the future. So this committee, it recommended the implementation of wide area monitoring system solutions across the country in order to measure the dynamic state of the grid and to detect the onset of any unstable oscillation events. So Ministry of Power then initiated a URTDSM project. This URTDSM project is Unified Real-Time Dynamic State Measurement Project, and PGCIL initiated the deployment of this wide area management system networks, and it was to be implemented in two phases. In first phase, around 11 1186 PMUs were to be installed, and in second phase, the balance left out 483 PMUs had to be installed in the Indian power grid. And then the data from these PMUs, as per the deployment plan strategy, where these PMUs are to be installed. So these PMUs are to be installed as per the optimal placement strategy of the PMUs. That is, the substation selection, it will depend on the applications of the measurements. That is, whether it is required for the state measurement or post-estimate analysis. So based on that, the PMUs will be installed in the grid. And in order to achieve full benefit of the PMUs, an architecture which involves the PMUs, communication links, and PDC and super PDCs that must also exist. So as per the deployment plan strategy of URTDSM, PMUs were to be installed. They will take one three-phase voltage, two three-phase currents, and 8 digital signals. And then these PMUs, they will provide three-phase voltage sequence voltages, that is both magnitude and angle, and three-phase positive sequence currents, both magnitude and current, the frequency and change of frequency. And this active and reactive power, this may be derived either at the PMUs or at the PDCs from the measured values. Now, as per this architecture, at the substations, these PMUs are installed, and then these PMUs, they are providing the information of the substations to the PDCs. PDCs are nothing but the phasor data concentrators, and these PDCs, they store the data which was available to them by the different PMUs, and these PDCs, they are the devices which are at the next level of hierarchy to the PMUs. So major function of these PDCs were to assemble all the data which was available to them through the various PMUs, reject any type of bad data which was available, and to align the timestamps if there is any mismatch, and to maintain a consistent record of all the data which is available from different PMUs. These PDCs, they also have a facility for local storage of data. Now, when we talk about the communication aspects of PMUs, all the PMUs for the communication system, this should be based on fiber optics. Even in the URT DSM scheme, this was the recommendation that all the communication system for the PMUs will be fiber optics, because if we are using fiber optics, we have higher data transfer rates, unsurpassed channel capacity, and these are also immune to any type of electromagnetic interferences. Hence, fiber optic links are widely used. When we talk about communication aspects, two data transfer aspects are also very significant. That is channel capacity. Channel capacity is nothing but the measure of the data rate which is sustained by the data link, and the latency in the measurement. Latency is time lag between the time the data is created and when finally it is available. So these two aspects are very significant for the communication aspect point of view of the phasor measurement unit. And when we talk about communication system, all the protocols, all the encryption techniques, they also come into picture. So when we have PMUs, the communication is serial communication by using RS-232, and all the PMU messages, they are mapped into TCP UDP or IP. For the performance point of view, the input signal of the PMU is when we talk about the PMU performance, we have an input signal to the PMU in the form of three voltage, current, and time inputs. And all these inputs, when we get the output is actually the phasor time tag is also attached to it, and it is the phasor estimate. There is a angle also, that is the phasor angle, that is also known as theta, which is the angle between the reporting instant and the peak of the sinusoid. And this magnitude, this is equal to the RMS value of the signal. Now, after giving the inputs to the PMUs, the input, they are also sampled, and number of filters are also used at the input stages. These filters, they sometimes cause phase delays into that. So along with this filters, some compensators are also used, so that any type of phase delay which is introduced by the filters, this must be compensated before reporting any phasor estimate of the PMU. So after giving the inputs, we get output in the form of phasor, which has a magnitude, RMS magnitude, along with it an angle. Now, when we talk about PMUs, three types of errors are permissible, or we talk of the errors in three quantities, that is total vector error, that is TVE, frequency error, that is FE, and rate of change of frequency error, that is RFE. So we will see about all these here. First one is total vector error. Total vector error is actually defined as the normalized value of the difference between the measured synchrophasor and the reference synchrophasor at the same instant of time. And these synchrophasor outputs, they have both amplitude and phase. So the synchrophasor reference value and the values which are obtained by the PMU, they may differ both in amplitude and phase. And this total vector error, it combines both the magnitude error and phase angle error into a single quantity. So in this, the reference phasor is denoted by X, and estimated phasor is denoted by X cap. So we can calculate the difference in between the reference phasor and the estimated phasor in the form of TVE. And this TVE, the maximum allowable TVE as per the all versions of synchrophasor standards for all types of performance test is 1%. Now, as we know that TVE is combination of magnitude error as well as phase angle error. So we can also calculate TVE if we know the magnitude error and phase angle error. And a time error of 1 microsecond corresponds to a phase error of 0.022 degree in 60 hertz system and 0.018 degrees in 50 hertz system. And if we consider that magnitude error is 0%, so a phase error of 0.57 degrees, that will cause 1% TVE, which is maximum allowable TVE as per any standard. And this corresponds to a time error of plus minus 26 microseconds for a 60 hertz system and plus minus 31 microseconds for a 50 hertz system. So magnitude, in the first figure we have the magnitude error estimation. So total, if we have no phasor angle, no phase error, then we can see as per this graph, if phase angle is increasing, how we can see the changes in the total vector error. Similarly, in the second figure, there is no magnitude error at 0 point, and when this is increasing, so allowable limit as per standard is 1%. So total vector error can be maximum up to 1%. So after talking about total vector error, next is frequency error. Frequency error is nothing but the difference between the measured frequency and the reference frequency, both measured at the same instant of time. And mathematically, we can say that it is the difference in between the measured and the reference frequency measurements. And next error which comes into picture is the rate of change of frequency error. And it is nothing but the difference between the measured rate of change of frequency error and the reference rate of change of frequency error. Both of them measured at the same instance of time. Now, when we talk about PMUs have different reporting rates as per the need of the application. And PMUs, they support different data reporting at different reporting rates. However, there should be multiple or sub-multiples of the nominal line frequency. And standard reporting rates for 50 hertz and 60 hertz system, they are shown in this figure. So for 50 hertz, the reporting rates are 10, 25, 50 or 100, which is as you can see are the multiple or sub multiple of the nominal line frequency, which is 50 hertz. Similarly, for 60 hertz, the multiples or sub multiples can be 10, 12, 15, 20, 30, 60 or 120. They are the standard reporting rates chosen for the 60 hertz system. Now, when we talk about phasor measurement units, they are classified into basically two different categories, that is P class PMUs and the M class PMUs. And they are classified in these two categories based on their application, whether they are used as P class, that is protection class PMUs, or M class, that is measurement class PMUs. The P class PMUs, they have shorter measurement latency time, and they have narrower frequency range, they have lower harmonic signal rejection requirements, and the applications are basically protection type of applications which require a fast response. Hence, they have a shorter measurement latency time. However, the M class PMUs, they are the measurement class PMUs which are required for the applications which deal with the measuring type. So they have longer latencies, they require more filtering for wider frequency range requirements. In this, we have increased harmonic and out of band signal rejection requirements, and these PMUs, they are used basically for the measuring applications. So basically PMUs are of two types, P class or M class, based upon their application in the grid. Now when we talk about the PMUs, we will have to see their standardization also, how they are standardized. So as these PMUs, they are installed in the grid, they are installed in the substations, and these PMUs, they are not of the same manufacturer. They are from different manufacturers and they provide data. So in order to achieve interoperability and to have PMUs which follow the standards, this standardization of PMUs came into picture. So as they are installed in the utilities, they provide the phasor data. So first of all, the organizations like NIST, they develop tests in order to characterize the PMUs and qualify them for the service. Because before this assessment, which was done by NIST in 2014, actual test results from these commercial PMUs, they were rarely seen in the public domain. So in 2014, NIST began assessing the performance of PMUs, both which were commercially available and some pre-production type PMUs too. So during 2014, a number of PMUs, as per this report which is available, between 9 to 12 PMUs, they commercial PMUs, they were tested by the NIST facility as per the standard which was prevalent at that time, that is C37118.1A. And it was a very surprising report that none of the PMUs, they were initially compliant to the standard. However, 3 of these PMUs, they subsequently managed to pass with some firmware adjustments, and 2 were reported being close to the passing limits. So based on these evidences, it is almost certain that any PMU which was purchased before or during 2014 and installed on the power network is not compliant as per the IEEE standard unless it has been carefully updated to that standard with any hardware or any firmware upgrades. And this public domain information, this information is available in the public domain in the form of the report which was published by NIST, and it provides a number of insights into the PMU behavior. But however, it is restricting in showing the generalized results in order to maintain the manufacturer confidentiality. So now when we talk about the test for compliance, whether the PMU is compliant or not, it will be determined by the quality of its hardware and the quality of its software. And the PMU software, it can largely be designed by using mathematical tools, and it can be tested in simulation in conjunction with the knowledge of the PMU hardware constraints, giving a very high fairly chance or higher degree of confidence that the PMU will behave appropriately. And these activities, they can be carried out at either at the manufacturer premises. However, in order to verify formally that overall the device performance, at least of a single device, is appropriate, these activities should be carried out in a formal environment at an independent PMU calibrator or a standard test setup as a test type. Also, it may be seen that every single PMU which is tested, it needs to be tested in order to verify correct calibration and operation of each single device, both at the manufacturer end or at the time of manufacturing and at specific intervals throughout the lifetime of each PMU, because temperature and aging can also affect and can cause drift in components that need to be periodically corrected for. Now, for this testing and calibration, for testing and calibrating any type of device, the test or calibration system, it should have an accuracy several times better than the device which is under calibration. And an order of 10 in accuracy is normally considered comfortable. So various PMU test and verification setups are run in the world by NIST, by Virginia Tech, by METAS, that is the Swiss Federal Institute of Metrology, the Fluke 6135A PMU calibration system, and there are some other facilities also, including those at Texas A&M University and a commercial device from Quanta. And of these setups, those at NIST and METAS, they are static systems. That is, they are fixed at their host locations to which devices must travel to be tested. However, the Fluke system, that is 6135A, this system is a racked system, that is, it is on wheels and it can be purchased and it can be used for testing in the field also, and it is an automated and by automation and by traceability of this system, test of PMUs can be done which require a testing time of less of around 6 to 12 hours per PMU. And at CSIR NPL, we have established this PMU calibration system, and this PMU calibration system established at CSIR NPL, it is traceable to the primary standards of the nation. Now, when we talk about these test and compliance of PMUs, different IEEE standards which are associated with PMUs, they come into picture. So the development of these standards started in early 1992. An IEEE working group was created in 92 by Professor Arun Fadke to formulate a standard in order to guide and to ensure that all the PMUs which are developed globally, they have compatible results. And hence the first standard for synchrophasors that was developed in 95, and it is known as IEEE 1344 1995 standard. However, this early standard, it only provided details about the signal samples, timing signal, and the communication protocol. But no measurement performance and accuracy requirements were specified in this synchrophasor standard. Also, in this standard, there was a discussion of the importance of time tagging and synchronization of each PMU and its sampling process to the UTC. However, in this standard, the time tag assigned to each report was defined as being coincident with the last sample which is taken in the data processed in order to create each report as shown in this figure. And this end of window time tagging, it brings lot of problems like the projection process made the measurements much more susceptible to sampling noise and any imperfect power quality. Also, quite different type of results they were perceived by different brands of PMUs, or even some identical PMUs, they were not showing the same results because they were using different algorithms or different window lengths or different window shapes maybe during their dynamic events. So such problems were associated with this standard. So for the improvement in this standard, again, this standard was revised and a significant improvement was seen over the 1995 standard in this standard, basically on the basis of the redefinition of the time tag in this 2005 standard. And in this, repositioning the time tag at the center of the window was done, which basically removes the need to project the measurement forward in time. with all the uncertainty that brings window center time tag placement, continues to be the most modern version of the standard. And this center of the window time tag is now referred to as the timestamp and also the reporting time. In this 2005 standard, along with this center of the window time tag or the timestamp, also known as the reporting time, along with this, the notion of total vector error, that is TVE, it was also incorporated in order to evaluate the phasor measurement requirements. And two compliance levels, that is level 0 and level 1, they were formulated in order to assess measurement accuracy over a range of magnitudes, frequencies, and phase angles. However, the main shortcoming of this standard was that it did not include any requirements for the dynamic operating conditions, and hence it could only be applied to the steady state conditions. So in 2011, this 2005 standard, this came apart to form two different standards, that is IEEE C37.1181 and C37.118.2. The C37.118.1 standard, it formed the measurement standard, whereas the .2 standard, it became the communication standard. In the measurement standard, the measurement and performance classes, they were included, and this performance class, the measurement and performance classes, they replaced the earlier compliance levels, that is level 0 and level 1. Also, the synchrophasor definitions and formulas were upgraded. For phasors, frequency and rate of change of frequency, it added specifications for the dynamic performance also, and testing over a temperature range, that was also incorporated in order to refine the requirements of the steady state performances. And the new measurement standard, that is point 1 standard, it included some other requirements like frequency ramp test. Along with it, the assessment of response time, which was related to the window length, was also included. Along with it, the delay time concept, that is accuracy of the alignment of the time tag to the window center, and latency, that is half the window length plus all the times for calculations and digital message generation and output, that was also included in this standard. Along with that, the undershoot and overshoot, they were also defined and tested during the amplitude and phase steps. So these were the basic refinements in this 2011 standard. Now, again, the main problems was, again, a revision of this standard was sought out in 2014. This revision to 2011, this was basically a revision to the 2011 standard, and this widened the rock-off requirements. Along with it, it suspended some of the rock-off performance requirements of the measurement class in presence of any interference of the out-of-band signal and harmonic conditions. Again, in 2018, a standard was published superseding the earlier 2011 standard. Now, this is the most current and the prevalent standard for the PMUs, and this is part of the IEC 60255 standard, and it is for the synchronized phasor measurement systems in the power system. This international standard, it defines a synchronized phasor, that is synchrophasor, all the frequency and rate of change of frequency measurements. It also describes the time tag and synchronization requirements for measurement of all three of these quantities, and it specifies the methods which are required for evaluating these measurements and requirements for the compliance with the standard under both static and dynamic conditions, and it defines a Phasor measurement unit, that is PMU, which can be a standalone physical unit or a functional unit within another physical unit. And this standard, when we talk about this 2018 standard, in this standard, for the frequency error and rate of change of frequency error, that is FE and RFE, they were expressed as signed values compared to the absolute value in the previous standards. So these signed values of errors, they are very helpful, as these values provide the grounds as well as all the nature of the error, keeping in mind that it has been changed in this. Keeping all this in mind, this has been changed in this standard. So when we talk about this, we talk about the compliance also. So compliance is all these PMUs which share data, they need to interoperate, and all the PMU users, they need to know that their data should be correct. So IEEE sets the standards for the compliance. All the accuracy and interoperability sometimes goes beyond the scopes of the standards. So test gears, they must be traceable to the national measurement institutes, and the results obtained, they should be repeatable, and they should be consistent between test locations. And the test procedures, they should be flexible, and they should also check for application specific limits. And for the IEEE also issued a guideline for the synchronization, calibration, testing, and installation of PMUs for power system protection and control. This is IEEE standard C37.242 2021 standard. It is the revision of the 2013 standard, and it provides the guidance which is required for the test and calibration procedures for PMUs for the laboratories and their field applications. When we talk about the test for the PMUs, we undergo different types of tests. Basically, they are divided into three categories, that is steady state test, dynamic test, and the latency test. In the steady state test, the input parameters like voltage and current, they remain constant, and these tests, they are carried out with a constant voltage and current inputs which are applied to the PMU under the test. So all the measurements which are carried out after the system stabilization, so in order to remove or rule out any transients, because we are talking about the steady state test. Whereas in the dynamic test, one or more input parameters, they are varied during the test period, and in this test, the magnitude or frequency of the input signal, it is either modulated or ramped, or step change of input signal is done in terms of the magnitude or phase which is being performed in this test. So basic, depending upon the different type of dynamic test, the magnitude or frequency of the input signal is changed. And in the latency test, the time delay from when an event occurs on the power system to the time it is reported in the data, it is being tested. So this latency, it includes many factors such as the window over which the data is gathered to make a measurement, the estimation method, the measurement filtering, and the PMU processing time, and when the event occurs within the reporting interval. So these three different types of tests, they are being carried out for the PMUs. And this CSIR NPL PMU calibration system, it was dedicated to the nation in 2018, and it is established against the primary standards of CSIR NPL. All the tests which are done by using the PMU calibration system, they are done from voltage range from 50 volts to 220 volts, and at currents of 1 ampere to up to 5 amperes at different reporting rates as per the requirement of the test. And this PMU cal system, as we are talking about its traceability, and as we all know that traceability is an unbroken chain of measurements which are traceable to the SI units. So main objective of having the traceability of PMU calibrator system is to ensure that all the PMU measurements, they are accurate, reliable, and are fully interchangeable. So the measurement traceability of the CSIR NPL PMU CAL system is established against the primary standards of the country. For the DC voltage, we have PJVS, that is programmable Josephson voltage standard. For AC voltage and current, we have multi-junction thermal converters, that is MJTCs. For resistance, the quantum Hall resistance standard is used, and for frequency, the cesium atomic clock standard is used. So PMU CAL system, the national feasibility, it is traceable to the primary standards of the CSIR NPL. So just to see a glimpse, this is the PJVS, that is programmable Josephson voltage standard for the DC voltage traceability of the system. These are the MJTCs for the AC voltage and current. For the resistance, we have the quantum Hall resistance standard. For the frequency, we have cesium atomic clock standards. So this chart, it actually shows the traceability charge of the PMU calibrator system. For the AC voltage range from 10 volts to 1000 volts, AC current from 100 milliamperes to 20 amperes, DC voltage 10 volts to 500 volts, DC current 100 milliamperes to 10 amperes, and frequency at 10 megahertz and from 40 hertz to 60 hertz. So we have this PMU calibration system. We are providing services to different manufacturers for their PMU calibration. Also, different representatives generally come from CEA in order to see what is this system and how it can be used for the nation. And we are also providing calibration services to PGCIL. Recently, we have calibrated the PGCIL's PMU calibrator system, which can be further used in order to calibrate all the PMUs. So that system is also now traceable to the national standards of the country. This is the setup of the PMU calibration system. In this way, we generate all the reports and data by using the PMU calibration system. All the inputs, they are time stamped to GPS. These are the results of long-term stability and analysis of measurement class of PMUs, which was done at NPL. These results are carried out for a period of 1 year, that is from January 21 to December 21, by using the CSIR NPL's PMU calibration system. And by these results, it is significantly emphasized that the CSIR NPL's reference PMU is very stable, and all the measurement results, they are in conformance with the IEEE standard. So for the evaluation and testing, this figure shows the front panel. In order to test the PMUs, we can have all the type of performance test for the steady state, dynamic performance test, and the latency test. So by using the PMU calibration system, the earlier picture was showing the front panel, so how we go for the test, and these shows the results which are obtained by running the test on a particular model of PMU. These shows the total voltage error, TVE, for a voltage positive sequence for a PMU which is being tested for the steady state test type. Again, these are the TV requirements for different phases of PMUs. It shows rate of change of frequency error. So I want to bring one thing also here, that although we have all these facilities, still the Central Electricity Regulation Commission of New Delhi, that is CERC, in a petition they said the URTDSM project, which is being implemented in India, this is having an overrun of 45 months and 37 months. And the time and the reason for the account of this overrun was shown as non-availability of testing facilities or testing labs for PMU as per the latest standards, whereas we have this testing facility still. CRC saying that non availability of testing labs is one of the reason because of the outrun of this project. So this should also be dealt with. So we have this facility still. Sometimes it's not known to the public. So by having such kinds of platforms, we can tell public also that we have these facilities and they should be used for the benefit of the nation. Also, we have carried out the reference PMU stability study for a period of 5 years in order to see its stability, and the results show that the standard is very stable and no drift is seen over the period of 5 years. From the time it was installed till now, it is very stable. The results of this were also published in APMP newsletter, and a news article was published on the calibrated phasor measurement units as a metrological tool for real-time monitoring of the Indian smart grid. And based on the feedback, now the first phase of URTDSM 1 project is over, and now the country is moving towards the implementation of the phase 2. So before that, a feedback on the URTDSM was published in March 21 by POSCO. So one main problem which was seen was that the PMUs in the Indian power grid, as we all know, they are multi-vendor. They are from different manufacturers and they have different levels of accuracy. So for phasor estimate, because the PMUs from different manufacturers, they are using different algorithms. So the phasor estimation methods they are using, that is different. So we are getting different results. So it is very difficult to draw any consequences from these different behaviors of the PMUs unless they are normalized on a common scale. This was also pointed by the POSCO feedback report. Therefore, to exploit in the WAM applications, all these PMUs from different vendors, they should provide consistent performance. So on the basis of this feedback, we are also undergoing a project, DST project, of 45 lakhs in order to carry out the metrological characterization of these PMUs from different manufacturers as per the latest IEEE standard for their effective implementation in the Indian power grid. Also, in this, assessment of various time synchronization sources will be conducted in order to ascertain the timing accuracy requirements for the synchrophasor applications in the power systems. Now, as we all know that we are moving towards the concept of realizing one sun, one nation, one world, one grid. So, because we are transitioning from a legacy monolithic power grid, which earlier consisted of a fewer power producers, and now we are moving toward a distributed and fragmented power grid, which will be based on a vast number of power producers, and it will be very diverse, will be having very diverse sources of energy with the integration of renewable energy sources also. So there is a need for implementing grid synchronization, and it becomes the prime importance and utmost importance. And effective grid synchronization can only be achieved if the grid and all its critical elements, they're accurately synchronized to a calibrated universal 1 TPS source. And the calibration and the data reliability, it can greatly assist the PMUs in order to pivot from being a purely monitoring tool to becoming a grid stabilization, grid automation, and an intelligent load management solution, which can be used to automatically isolate the problem areas which are extensively loading the grid by monitoring the deviation in the phase angles, phase shifts at various points. And by effectively using a PMU which has been calibrated to the national standard can be used to achieve and effectively ensure an efficient and a stable national power grid. So I would like to conclude by saying that the methodology for testing and calibration, it can be adopted by the PMU manufacturers by, by calibrating the PMUs from the different vendors in order to check their performances before deploying these devices in the smart grid for reliable infrastructure. And it is also significantly emphasized that the CSIR NPL reference phasor measurement unit is highly stable, and all the measurement results, they are well within the limits and are in compliance with the IEEE latest standard. And this stable PMU, it is used as a reference standard in order to check and compare the performance of the PMUs under the test. And the researchers from this field, they can also use this methodology of PMU testing in order to check the compliance and reliability of the PMU models which are developed by them as per the IEEE standard. Also, the CSIR NPL's PMU calibration system, it is established against the primary standards of the country, and in order to ensure reliability and accuracy of the acquired data, all the PMUs, they should be calibrated, and CSIR NPL recommends to the NPC also that in order to ensure this, every PMU, it should be calibrated from a traceable PMU calibration system before their deployment in compliance with the IEEE standard. And we need to calibrate PMUs in phase and amplitude from the different brands that are being purchased in India and are in the electricity grid. And periodical calibration should be done in order to avoid any power outages and cascading blackouts, minimizing economic losses to the country. And with these traceable measurements, all the PMUs which are deployed will be helpful in obtaining accurate and uniform data in order to increase efficiency, improve reliability, and enhance the quality of the power grid. These are various references which are being used. So also the North American interconnections or the electrical transmission grid, which operates as a hugely complex machine, they also say that measurement tools at the heart of smart grid, they need calibration in order to ensure reliability. And Alan Goldstein, who is working for the PMUs at NIST USA, he stated that worldwide agreement that calibration is needed, and in order to provide compliance limits and test methodologies to ensure performance, conformance, and interoperability is required. So, for any developed country, a developed country will be one in which we will have developed metrology, and metrology is must for science and technology, and we need vision and dedicated efforts in this direction. And all these accurate measurements, they will make science more scientific, technology perfect, environment clean, energy sustainable, healthcare affordable, cybersecurity strong, international trade barrierless, and all our policies nation building. Thank you so much.
Thank you very much, ma'am, for your brief and kind explanation of this very important topic related with the power grids. How we will do in future, after listening this all, as we are all aware, it is basically related with large number of things, because you need the voltage uncertainty, current uncertainty, and then the time uncertainty with the frequency uncertainty. So considering all these uncertainties, it is very important. And I hope that certainly the participants who are listening these topics, they will be benefited from this presentation, brief presentation. And certainly if there will be any requirement, we will again request you to come. Santoshji, if you are here, Santoshji, are you here? Okay. In the meantime, as we have with us Sanjeev Kumarji from IDMI, I'd like to request him to speak 2 words about his experience and knowledge, so that our participants can be benefited.
Yeah. Good afternoon. Myself, Sanjeev Rasal. I was ex-MD of IDMI Mumbai, which is one of the having a best calibration lab in the electrical parameter. So wherein we were doing a lot of power and energy calibration. So I can say only that this topic, power grid, which was initiated by Dr. Ashutosh Agarwalji and presented by Madam. It is really interesting to these participants and they must have enjoyed. Nowadays, a lot of automation is going on in this power grid system and a lot of softwares have been developed. I have seen this thing at VGTI Mumbai, wherein I think Siemens has installed one software and they are doing a lot of work on that. So only I know that much, but I think the participant can take benefit of such things, and definitely such initiations will be benefited to the industries and the entrepreneurs and do some research assistant also. They will get benefited by this thing. And thank you very much for giving me opportunity. I was here for NABL audit with Dr. Ashutosh Agarwalji. So, and I hope, wish you all the best and thank you very much.
Thank you, sir. Thank you for your brief introduction. We have with us Dr. Gautam Mandal. I'd like to request him to speak at least 2 words, please.
Very good afternoon to all. So myself, Gautam Mandal, Senior Principal Scientist at CSR National Physical Laboratory. And thanks to Ashutosh ji for giving me opportunity. And he is doing nice job, really, even every week, every Saturday. He organized this training program for benefit of the nation. And also I have personally delivered 3 lectures on weighing balance and weights also, and on 2 methods, subdivision method and substitution method. And also I have responsibility of Deputy Quality Manager as per ISO IC 17025 and ISO 17034. So there are 28 subdivisions of CSR NPL under quality system, and definitely electrical parameter is one of them. And personally, I know Dr. Abni. She is doing nice work. So thank you very much, and definitely it is very helpful for the participant and for the nation benefit, because CSR NPL is National Metrology Institute of India, and we are doing our level best to maintain the national standard as Government of India has given responsibility to be the National Metrology Institute, and we maintain the various physical parameters. Either it is mechanical parameter or electrical parameter, time frequency, all the physical parameter except ionizing radiation. So this is our responsibility to maintain the national standard at the highest level of the nation, and at the same time we have responsibility to disseminate it to get benefit of the nation, to improve the quality infrastructure of the country. So thank you very much. Thank you, Ashutosh ji. Thank you.
Thank you, Dr. Gautam Mandal. It's a very great opportunity that you people are here, and you can also certainly, you have already given many lectures. I'll request Dr. Sanjeev Kumar to please be with us, and certainly we will use him and we'll take his help for disseminating information. Now, I would request all the participants to kindly switch on their videos and switch off their mic, please, so that we can take a picture to place it on our Twitter handle, WhatsApp handle, Twitter handle, this Facebook, as well as this Instagram, and all portals. And certainly it will be a very good experience for all of us. Santoshji, please kindly take a few of the pictures. My request is all the participants to kindly switch on their video, please.
Today I am here on behalf of NABL for the NABL assessment of mass and weighing balance. Myself and sir.
Myself, Sanjeev Prasad, I am also today here for NABL audit.
For the NABL assessment.
Sir, would you like to say something? Dikshit sir?
This is very good program we have done, and the participation like Dr. Mandal and from NABL side, your friend. So that is very important for us that they have come today to the RSL Ahmedabad and from their busy schedules. And we give thanks to Dr. Saab also. He has given a very good presentation on the grid and this integrations and the transformations, transfers, and that dissemination to common consumers and the industry requirement and how the industry can make their best. And in the meantime, he has requested that those who are doing the best, because at present we have less facility in our country, so they must not be disturbed. So we must appreciate her views and her knowledge, and we may keep calling her Dr. Khetkar Madam near future programs also. And we may express our thanks to Director ABL also, and because he has given a lot of opportunity of their scientists time to time to come into the programs and to participate in the programs. And we are very thankful for his support and hope that in future the alignment of NPL, RSL, and the legal metrology will continue to develop the country in the best positions. And I thanks to I congratulate Mr. Agarwal to visit the Switzerland and to participate in that project program of PIML and OIML.
Thank you, sir.
And where he has reported the Indian situations and the progress of the laboratory, and that at present India is not that old that country where the laboratories are not very progressive. We are taking every steps where the laboratory may get the progress, industry may get the progress, and to take the challenges of the international opportunity. So on my behalf and other participants, if I agree, I give thanks to all the participants. Thank you, Dr.
Thank you
Ashutosh,
very much, sir.
Dr. Mandal.
Thank you, sir.
And,
Thank you very much for your kind words. Sir, actually, you know, the new rule which was supposed to be implemented from 1st of April 2022-23, we have again extended for 2 more months. And now it will come into force for this unit sale price and some other more declarations on the pre-packaged commodities. Now it will come into force from 1st of June 2023. So 2 months extension we have given considering the request of the industries. This is the information which I wanted to share, and it is available on our website. With this, I would like to thank all the participants, Dixit sir, Dr. Avani, who has given this presentation, Dr. Gautam Mandal, Dr. Sanjeev Kumar, and my all participants with NIC team who has made this program successful. With this, thank you all.